Hi, good morning. Am I audible?
Yes, sir.
Yeah.
Good evening, everyone. I'm Sneha Sir, Assistant Professor, Computer Science and Engineering at Sridevi Institute of Engineering and Technology, Tumkur. It's my privilege to introduce our esteemed industry expert for today's quantum technology session, Mr. Vikas Yetnali, who joins us as a lead engineer from Quest Global Bangalore. Vikas Etnaliso comes with a robust academic background, hold a BE in Electronics and Communication Engineering and an MTech in Digital Communication. He brings over 13 years of extensive industry experience, making significant contributions to engineering advancement and real-world technology solutions. His qualifications includes global certifications such as AWS Certified Solutions Architect, Associate, AWS Certified DevOps Engineer, Professional, Microsoft Certified, Azure Administrator Associate, and Microsoft Certified DevOps Engineer Expert. Vikas Etnali's technical expertise covers both AWS and Azure Cloud Platform and key DevOps and automation tools like Jenkins, Git, Docker, Kubernetes, and Terraforms with a special focus on infrastructure automation and CI/CD pipelines. He has played a leading role in a project for the healthcare, banking, and e-commerce domain, each demanding advanced, scalable, and secure solution. Vikas Etnal is a combination of strong academic credential, respected certification, hands-on industry exposure, and leadership in mission-critical projects makes him the ideal person to launch today's technical discussion. Let us give a warm welcome to our first resource person, Vikas Etnali, sir. Sir, the session is yours. Thank you.
Thank you very much, Sneha, for kind introduction. Thank you all for attending the session. Very good evening. So let me share my screen. So let me know once the screen is visible, everyone. Is the screen visible? Can someone acknowledge?
Yes, sir, it's visible.
Okay, fine. We will begin off from here. Uh, so to begin with introduction to quantum communication systems. So quantum communication basically uses quantum mechanics states, typically single photons, to transmit information securely. Unlike classical bits, qubits can exist in superposition and can be entangled across distance together with no cloning theorem. These features make eavesdropping inherently detectable and shift security from computational assumption to physical laws. So, a practical quantum link comprises a source and encoder that prepares polarization, phase, or time bin states. A quantum channel, such as optical fiber or free space, highly sensitive single photon detectors with finite efficiency and dark counts, and an authenticated classical channel uses for shifting, error correction, and privacy amplification. In double B84 protocol, basically, let's assume Alice sends random encoded photons, and Bob is a receiver, and Bob measures in randomly chosen bases. Then later, they later reveal only the basis, keeping the matches and estimate a quantum bit error rate. If it is low, they reconcile difference and compress the key to remove any leaked information, yielding a shared secret. Throughout this course, we will treat quantum communication as an augmentation to classical networks, and it prioritizes security over throughput, is range limited today, and unlimitedly aims at repeater assisted wide area quantum networks. So, quantum communication systems are next generation of secure networks in which protection is rooted in the laws of quantum physics rather than in computational assumptions. So instead of relying on the hardness of the problems that a future quantum computer could solve, these systems achieve provable information theoretical security and attempt to observe the transmitted quantum states inevitably leaves a detectable disturbance. In practice, basically, information is carried by carefully prepared quantum states of light, typically single photons, which properties such as polarization, phase, or time been encoded the symbols. Because of superposition, entanglement, and no cloning theorem, an eavesdropper cannot copy the states perfectly or measure them without changing them, which allows legitimate users to detect interception by monitoring the induced error rates. So, to continue on, it is helpful to contrast this with classical communication. Classical links also use electrical or optical signals, as we know, but those signals contain many indistinguishable photons and can be amplified, copied, and measured without intrinsic disturbance. Security therefore depends on cryptographic algorithms and key lengths. But in quantum communication system, by contrast, the physical layer itself participates in security, which is a big gain here. A typical deployment uses a quantum channel, fiber, or free space to send the fragile photon states, and an authenticated classical channel for post processing steps such as shifting, error correction, and privacy amplification. The outcome is shared secret key whose confidentiality do not degrade even against powerful advertisers, including quantum computers, making QCS a strategic complement for existing network infrastructure. And to begin with the fundamentals of quantum mechanics, on this slide I will introduce you basically three principles here that makes quantum communication possible. These are not abstract curiosities; they different determine how we encode symbols, why interception leaves traces, and how keys can be distilled securely. So the first one will be superposition. This is a quantum bit or a qubit which we call can be prepared in a combination of basic states at the same time. A helpful picture is a coin spinning in the air. Before it lands, it is not possible purely heads or tails. So, when a qubit prepared in superposition is finally measured, the act of measurement forces a single definite outcome and irreversibly destroys the superposition. Because outcome depends on the basis used for preparation and the basis chosen for the measurement, we can encode information in non-orthogonal and ensure that the unintended measurement collapses and introduces errors. This is exactly the lever used in protocols such as BB84. And next one, coming to entanglement, when two or more particles are entangled, their measurement outcomes are correlated more strongly than any classical model allows. Basically, measuring one immediately defines the statistics of the other, even when the particles are widely separated without enabling faster than light signaling. Entanglement underpins entangled basic QKD such as E91 protocol, enables quantum teleportation, and is the resource from future quantum repeaters will use to extend secure links over long distance through entangled swapping. And the last one would be Heisenberg's uncertainty principle, which you most might be aware of. Here, certain pairs of observables like position and momentum or two conjugate polarization bases cannot both be known precisely at the same time. The more accurate one is determined, the less precisely the other can be predicted. For communication, this means that an eavesdropper measuring in the wrong basis inevitably disturbs the state, increasing the observed quantum bit error rate. Combined with the no cloning theorem, uncertainty guarantees that copying of probing unknown quantum states without detecting is fundamentally quite impossible. Taken together, superposition, entanglement, and the uncertainty, which we looked into right now, explains why quantum links can reveal tampering at the physical layer and why we always pair the fragile quantum channel with the classical authenticated channel to complete the security workflow. Going further, we will better understand what is a quantum bits. So quantum bits or qubit, what we call, is a quantum analog of a bit. Instead of being strictly 0 or 1, qubit can be prepared in the superposed state written as alpha times plus beta, alpha times 0 plus beta times of 1, which we basically use, where we squared magnitudes of alpha and beta sum to 1. When we finally measure the qubits in the chosen basis, we obtain a single classical outcome and the superposition is destroyed. This does not mean a qubit carries unlimited data per symbol. Rather, the advantage comes from how superposition and measurement disturbance can be exploited for tasks such as secure key generation and interface based protocols. In photonic system, basically, qubits are encoded in a physical degree of freedom such as polarization, optical phase, or time bin arrival. Many experiments, such field trials, use entangled photon pairs, typically produced by spontaneous parametric down conversion in a nonlinear crystal. Entanglement gives correlation stronger than any classical source and enables entangled base QKD as well as future repeater architectures. In prepare and measure schemes like which BB84, where we do not require entanglement, we prepare single photon states in random chosen bases and rely on measured disturbance to reveal eavesdropping. So basically these fragile transfers a quantum channel, either optical fiber or maybe a free space. The key impairments are attenuation, depolarization or phase shift and environmental noises, of all which raise the observed error rate. At the receiver, single photon detectors, silicon avalanche photodiodes or superconducting nanowire detectors are used, converting individual photon to electrical clicks with finite efficiency, time jitter, and occasional dark counts, which we usually observe. Practical system therefore combine careful state preparation, stable channel, time synchronization, and authenticated classical post processing to extract a reliable, a secret key, and inherently probabilistic measurements. So going further, uh, okay, we will understand this quantum entanglement and Einstein's spooky action at a distance. So quantum entanglement is a joint state of two or more particles in which the whole cannot be described as a sum of its parts. Measurement on one particle are correlated with measurement on its partners more strongly than any classical model basically allows. Importantly, these correlations do not enable faster than light signaling. Rather, they reflect non-classical joint statistics revealed when outcome from both sides are later compared. Two operational features matter for communication are non-local correlation. Example, if Alice and Bob change measurements based independently, their outcome exhibit pattern that violation of Bell inequality, for example, the CHSH test, which we call. Such violation certifies that the correlation cannot be explained by pre-existing classical information and implies security against a broad class of attacks. Random and correlated the results. Each local outcome looks random, but paired results are predictably related to once the measured setting are known. That is like resonance under the exact shared keys. In practice, basically, entanglement is generated using sources such as spontaneous parametric down conversion or quantum dots, producing photon pairs entangled in polarization time bin on energy time. The pair are distributed over fiber or free space channels to distinct nodes basically. Loss which we observe, phase drift and decoherence reduce the observation correlation quality. So system employ active polarization or phase shift stabilization, tight time synchronization and high efficiency single photon detectors. For networking basically, entanglement enables entanglement based QKD, the examples include E91 or BBM92, where security is certified by Bell test statistics, quantum teleportation, which transfer unknown states using classical message plus shared entanglement. The entanglement swapping a building block of the quantum repeaters that will extend secure links to the containment scales. So going further, we will understand what is quantum key distribution, which we basically also call it as QKD, which I referred in my previous slides. It basically establishes a shared secret key whose confidentiality is guaranteed by quantum physics rather than the computational hardness. Information is encoded on quantum states on single photons, typically in polarization phase or time bin, and sent over quantum channels because of measurement disturbance and then non-cloning theorem. Any eavesdropper who's coming in inevitably introduce detectable errors. In this canonical basically double B84 protocol, which was basically introduced in 1984. Let's again take an example of Ellis and Bob. Ellis prepares states at a random in two conjugate bases while Bob measures in random chosen bases. Over an authenticated classic channel, they then reveal only the bases, keep the matched subset, which we call shifting, estimated the quantum bit error ratio to test the eavesdropping, and if it is below a threshold, apply the error correlation and privacy amplification to distill a uniform random key known only to both of them. Practical deployments often use weak coherent light with decoy states to defeat the photon number splitting attacks, along with high efficiency single photon detectors. So, entanglement based variants certify security through Bell inequality violations, and the distilled keys typically refresh symmetric encryption or in niche cases drive only one pad. Engineering limits today include channel loss and detector imperfections, which are unavoidable, motivating the trusted node relies satellite links and long-term quantum repeaters. Thus, QKD or quantum key distribution complements rather than replaces classical cryptography and is being explored for high-value applications in finance, defense, government, communications, and intercity or satellite networks as well. So we will go for quantum key distribution, securing communications with physics basically. So as you can see, quantum key distribution leverages the laws of quantum mechanics to create encryption keys whose secrecy does not rest on mathematical difficulty. Instead of assuming that factoring a discrete logarithms remaining hard, QKD offers information theoretic security. Any attempt to observe the quantum state used to establish the key inevitably changes and leaves a measurable trace. In operational terms, QKD enables two parties to generate and leaves a shared, unfortunately, uniformly and also random secret key and to refresh it frequently. The key that protects ordinary data channels using a one-time pad of modern symmetric ciphers under idealization models and with an authenticated classic channel, security holds even against advertisers and future quantum computers. The mechanism is simple to the state. When an eavesdropper probes the quantum signals, the no cloning theorem and the measurement disturbance raised the observed error rate, allowing the legitimate users to detect the intrusion and abort. This is why QKD is often described as providing eavesdropping detection also at a physical layer. The complementary entanglement based approach is a E91 protocol, which I had mentioned before, which distributes the entangled photon pairs to the two users. There, the security is certified by Ben equality test, which I mentioned, is a measured correlation violation and then the classical bound. The users can trust the no hidden classical information explains their outcomes. If the violation degrades beyond the threshold, they infer tampering or excessive noise and discard the data. In short, QKD provides unbreakable security in principle, a practical method to exchange fresh symmetric keys and built-in alarm when inception is attempted. Next, quantum key distribution protocols. This slide introduced basically I had been like referring before BB84, the first practical quantum key distribution protocol proposed in 1984 by Charles Bennett. This their motivation was very clear. Classical cryptography bases security on computational hardness, assumptions that can be weakened by faster hardware or new algorithm, including quantum algorithms. Both of them asked whether the physics of information could guarantee secrecy information. Two quantum facts suggested a path forward for them. Unknown quantum states cannot be cloned perfectly, and any measurement of state prepared in the incompatible basis will disturb in a measurable way. So, BB84 turns these facts into a key exchange model or a method. Let's say Alice prepares single photon at a random in one of the conjugate bases. You can picture them as a recliner and a diagonal. Bob measures each incoming photon into a random chosen basis of his own. Later, over an authenticated channel basis, they publicly announce only the basis which they are used, discard the event when their base different, which is shifting, and keeping the rest of their raw key. By comparing a small randomly selected subset, they estimate the quantum bit error rate. Any eavesdropping who tries to read the photons without knowing the basis inevitably introduces extra errors, obviously. In if the observer error rate is below the protocol specific threshold, Alice and Bob run error correlation and privacy amplification to distill the shared uniform random secret key. BB84 basically the blueprint of modern QKD. Practical system often use weak coherent pulse with decoy states to defeat multi-photon attacks, and later protocols such as E91, BBM92, SARG04, and continuous variable QKD extend the same core idea to different physical encoding and security proofs. Okay, we'll start like again. We'll try to understand the BB84 protocol. This was introduced, as I told you, by Benetton and Brassard in 1984. Turns quantum physics into a practical key exchange method. Alice encodes, as you can see in the diagram, Alice encodes random bits onto a single photons using one of the two conjugate bases. Think rectilinear and diagonal. The Bob measures each photon into a random chosen basis. After transmission, they publicly reveal the basis, discard the mismatching shift, and keep the matches as a raw key. By comparing a small sample, they estimate the quantum bit error. Any eavesdropper unable to copy or measure the unknown states without disturbance necessarily raise the error rate, obviously. If it is below the threshold, Alice and Bob run error correction to align their strings and privacy amplification to remove any leaked information, yielding a shared secret key. In practice, system uses weak coherent pulses with decoy states to foil multi-photon attacks and encode information in polarization phase or time bin. BB84 remains till date the simplest and most widely deployed prepare and measure QKD scheme. Like how QKD basically works in to be explained is It's establish a secret key using polarization photons. Key generation, Alice sends a randomly encoded photon. Bob measures each with a randomly chosen basis. Basic recollection happens. After transmission, they publicly reveal, as I mentioned before, only the basis used, discard the mismatches, and keep the matches as a raw key. And in this eavesdropping test, which happens, any interaction, like interception, disturbances, the states raised, and observed quantum bit error rate. If the rate exceeds a threshold, the run is aborted, obviously. And error correlation, Alice and Bob reconcile remaining discrepancies over a authenticated classic channel. So privacy amplification happens, then they compress the reconciled string to the shorter uniformly random key, that is information theoretical secure. The result is a frequently refreshed and symmetric key that protects ordinary data traffic. So, to introduce the E91 protocol, it was proposed by a person called as Arthur Ackert in 1991. Is an entangled based form of QKD. A source creates pairs of entangled photons and send one to Elise and one to Bob. Each independently chooses a measured basis, where they later compared only their settings. The result correlation should be violate a Bell inequality, or typically CHSH, if genuinely entangled is present. The violation is basically security test. An eavesdropper or any person noise reduces the violation, so the user abort when it falls back to the threshold. From the subset of setting pairs that are maximally correlated, here Alice and Bob forms a raw key, and then run error correlation and privacy amplification to obtain a simple key. Unlike BB84E91's security is tied to observe non-local correlation and place less trust to the source. Stronger variants lead towards device-independent security. In short, E91 turns belt test physics into a practical, tamper-evident, and key exchange method. So E91 step-by-step working, if you have to decode, a source create a pair of entangled photons and delivers one to Alice and one to Bob over a fiber or a free space maybe. For each pair, Alice and Bob independently choose a random measurement base from present angles and record the binary outcomes. After many trials, they publicly reveal one of their settings and keep the subset with compatible choices as a raw key. The rest is used for testing. From the test subset, they compute a CHSM Bell inequality value. A clear violation certifies genuine entanglement and rules out the undetected interception, whereas low value signals noise or eavesdropping, and the run is basically aborted. If the violation is adequate, they perform error correlation to align the strings and privacy amplification to compare any leak information, yielding a secret key. Security here is anchored in the observed non-local correlations, so even an untrusted or an imperfect source cannot pass the belt test without real entanglement. So going further, we'll go to the E91 protocol. As I mentioned before, it generates secure keys from the entanglement. A source creates the photon pairs and sends to Alice and Bob each one of them. For each pair, they independently chosen a random measurement basis, typically from three angles, and record a binary outcome. Afterwards, they reveal only their settings, keep the compatible subset as a raw bits. From the test subsets, they compute a Bell inequality value. A clear violation certifies genuine entanglement and rule out the undetected interception. Failure to violate indicates noise or eavesdropping, and the run is discarded basically. When the violation is adequate, they extract a key by applying the error correlation and privacy amplification. Thus, in E91, Security is tied to observe non-local correlation rather than trusting the source, making it a robust entanglement-based alternative to BB84. So next up, like discussing the no cloning theorem. Here, no cloning theorem basically states that it is impossible to make a perfect copy of an arbitrary unknown quantum state. If the universal deceived mapped and linearity of quantum mechanics would be violated because inner products must be preserved, non-orthogonal states cannot be duplicated without contradiction. So practically an attempt to copy an unknown state amounts to a measurement in some basis and therefore disturbs the state, an expression of the uncertainty principle. For communications, this has two consequences. An eavesdropper cannot split the signal, clone the qubits, and learn the key later. They must measure now and thereby raise the error rate. The physics impossibility of undetected copying is a cornerstone of QKD security, and the reason decoy state methods are used when weakened coherent pulse occasionally emit multiple photons. So next up, we have no cloning theorem. The next slide, where why is QKD is theoretically unhackable, which they say. So the no cloning theorem says an arbitrary unknown quantum state cannot be perfectly copied. In QKD, this means an eavesdropping Eve can, let's say his name is Eve, cannot duplicate or split the photons to learn the key later. Any attempt to probe them forces a measurement and disturbs the state. The disturbance appears as a higher quantum bit error rate, which Elise and Bob estimate over the authenticated classic channel. If the error exceeds a threshold, they abort and discard the data. If not, they proceed with error correlation and privacy amplification to obtain a secret key. Because like perfect copying is forbidden for physics, not just by math, store now and decrypt later attack fail. Under standard assumption, like trusted devices and authentication, QKD keys integrity is therefore secured by physics law here. So next, practical implementations and current technology. Uh, QKD has moved from laboratory demonstration to pilots now. Over fiber metropolitan testbeds, distributed keys across existing dark fiber or wavelength division multiplex links range is typically limited by optical loss. So trusted immediate nodes are used for intercity spans. Satellite QKD overcomes ground fiber distance limits by sending photons through the atmosphere and space. Where loss is lower, downlink passes the enable country to country key exchange and time limited key refresh. Finally, integrated photonics is miniaturized resources, modulars, and detectors on the chip scaling platforms, improving stability and enabling lower cost field deployable devices. In practice, all deployment pair the quantum links with an authenticated classic channel, performing shifting, error correlation, and privacy amplification, which I had mentioned before, and then feed the distilled keys to conventional encryptors that protect user traffic basically. So challenges, distance limits and hardware vulnerabilities basically. So QKD is theoretically robust as we all know, but three practical hurdles dominate here. One is distance. So fiber loss caps unaided links at approximately 100 to 200 kilometer. Intercity system relies on trusted nodes today. Satellite extends reach and true scalability awaits quantum repeaters. Speaking of hardware vulnerabilities, device imperfections, open site challenges, example, detector binding, timing space leakage, migration including decoy states, careful calibration, and measurement device independent QKD. And last one is cost and scale. Its specialized sources, low noise detectors, and integration with key management raise cost. Near term adopted targets high value links while integrated photonic drive price down. So next up, we'll speak of quantum teleportation. It does not quantum teleportation does not move matter. It transfer an unknown quantum state from a sender to the receiver using shared entanglement and a small amount of classical communication. Again, let's speak of an example. Alice performs a Bell state measurement on the state to be sent on her uh, half of the entangled pair, then sends two classical bits to Bob. Based on those bits, Bob applies one of four unitary correlation and reconstruct the original state on his qubit, while Alice originally is destroyed. Fully consistent with the non-cloning theorem and with relativity no faster than light signaling. This mechanism is building block of quantum repeaters and entangled swapping, enabling long distance quantum networks, and it supports future distributed quantum computing and also quantum sensing. Practical demands include high fidelity entanglement, reliable Bell measurements, tight time synchronization, and low loss channels. Okay, and next up, quantum teleportation, transferring quantum states over the distance, which is a challenge always. So, quantum teleportation transfers are unknown quantum states, as I told you, not the particle between distant particles. So, as we again speak, Alice and Bob first share an entanglement. Alice performs a Bell state measurement on the state to be sent on her half of the pair, producing two classical bits basically. She sends those two bits to Bob while Bob applies the corresponding unitary correlation and recreates the original state on his qubit while Alice's copy is completely destroyed. This process obeys a non cloning theorem and never enables faster than light signaling. This capability underlies entanglement swapping and quantum repeaters for long distance networks and support future distributed computing and precision quantum sensing. High fidelity entanglement, reliable Bell measurements, and tight synchronization are the key practical requirements. And basically, current challenges, decoherence, and the quantum memory problem is what is the current challenge. So, quantum states are very fragile. The loss, the phase noise, and the polarization drift in channel and compute cause decoherence, raising error rates and limiting the range. To build larger networks, we need reliable quantum memories that store photonic qubits on demand and release them with a high fidelity, long coherence time, and good efficiency, which is a prerequisite for quantum repeater. Today's leading candidates, let's say cold atoms, NV centers, rare earth, doped crystals, still trade off lifetime, bandwidth, and multiplexing. They keep on fighting between these three parameters. The remaining challenges is a scalability, chaining many nodes, demanding stable sources and detector, precise timing and synchronization, robust calibration, and integration with key management and classical control. Progress is coming from better materials, dynamic decoupling, and early error correlation techniques, but overcoming decoherence and deploying practical memories are the central hurdles to wide area quantum communication. And let's speak next of the real world applications basically. So, real world applications in terms of satellite QKD or satellite communication. QKD suppliers tamper evident keys for sensitive government, diplomatic, and intelligence links, strengthening a long term confidentiality. And in terms of banking and finance, it protects interbank backbones, exchanges, and HSM key injection workflows, providing quantum resilient key refresh for payments. which is a real good breakthrough. And in military and defense, quantum secure command and control prevents undetected in in sorry, give me a second. So in military and defense, it provides an undetected interception of copying the mission traffic, interfusion raises and Kuber and trigger aborts. And in satellite and space, satellite QAD overcomes fiber loss to enable country to country keying. Example, to be speaking, recent one, China's MICI US intercontinent demo, which was in 2017, and ISRO free space trials, which was run in 2021. Healthcare and data privacy. QKD hardens EHR networks and telemedicine backbones, ensuring confidential transfers of medical records. So, next up, speaking of the future of quantum communication, and I already spoke of these applications. Speaking of the future of quantum communications towards a quantum internet, the long term goal is quantum internet basically. A network, quantum internet is a network that distributes and manipulates entanglement across many nodes. Such a fabric would be providing povable security communication beyond classical encryption, enable distributed quantum computing by linking small processors, and support federate quantum sensors with unpredicted precision. Achieving this requires quantum repeaters built from high fidelity entanglement swapping and quantum memories. Also, plus error migration, time synchronization, and an integrated classical control plane. The near term roadmap is incremental metropolitan fiber link, satellite trunking, and memory assisted repeaters, converging towards interpolable standard based networking. While challenging is loss, memory lifetime, and cost remain sustainable, progress indicate a clear path of scalable, tamper evident, and connectivity, a new scientific capability. So, speaking of advantages of quantum communication, which securing our future, quantum communication matters now for basically three reasons. First, the threat. Scalable quantum computers endanger today's public key cryptography, creating a harvest now, decrypt later risk. The second one would be the response. QKD and related techniques provide keys whose secrecy rests on physics, complementing post-quantum cryptography to form a layered forward secure posture. And third one would be the momentum. Sorry, governments and industry worldwide are funding pilots and standards, accelerating standard links, metro fiber testbeds, and integrated photonic devices. The practical takeaway is to plan hybrid deployments, integrating QKD with modern key management and PQC, so critical system gain long-term confidentiality before adversaries catch up. So next up, unbreakable security, the power of quantum key distribution. QKD basically generates encryption keys whose secrecy is guaranteed by physics rather than the computational assumption which I had hinted before. Because unknown quantum states cannot be cloned and incompatible measurement disturb them. Any attempt to tap the photon stream raises the observable quantum bit error rate, which is a QBER, and is immediately detected. After transmission, Alice and Bob reveal only their basic choices over an authenticated channel, discard mismatches, and test a sample for excess errors. If the threshold is exceeded, they abort. If not, error correlation and privacy amplification produces a shorter, uniform, random secret key. The result is tamper evident keying that defeats harvest now, decrypt later strategies and robust protects conventional and encrypted traffic. So, coming of the future landscape, integrating QKD into global security infrastructure, QKD is best viewed as a foundational layer in the modern quantum resilient security stack. Hybrid solutions basically combine QKD for physics backing key with the post quantum cryptography, which is called as PQC for scaling and software flexibility, keys and QKD feeding existing KMS HSM workflows. Quantum internet, memory assisted memory assisted repeaters and satellites will extend coverage from metro fiber to global links, enabling routine intercity and intercontinental key refresh. So standardization, profiles and interoperability testing of protocols, interfaces and devices security together with certification against side channel attacks are essential for procurement and multi-vendor deployment. Resilience because secrecy does not rely on computational assumptions, as we all know. QKD provides long-term horizon confidentiality and migrates harvest now, decrypt later risk. The practical roadmap is phased adoption, pilot critical link integrated with PKI PQC, and scale as hardware cost and performance improvement. Next up, resistance to eavesdropping, quantum physics as a guardian, which we have to speak. So, quantum mechanics itself provides the defense against interception because unknown quantum states cannot be cloned, and any incompatible measurement disturbance the states. A passive tap cannot copy the photons used for key exchange. In practice, the disturbance appears as an elevated quantum bit error rate during the public test phase with an authenticated classic channel. So here Alice and Bob detects an anomaly and abort, making undetected eavesdropping very much infeasible here. This is not merely theoretical. Multiple European and US projects have demonstrated QKD across uh, diverse fibers and free space links, validating tamper evident performance outside the lab. At global scale, trials with China's um, MIKI's satellite have shown satellite to ground QKD over around 1200 kilometers, proving the quantum secured links can span long distance when atmospheric and space losses are managed basically. So next up, future proof technology, which is ready for the quantum computing area. So classical public key cryptography rests on problems such as factoring and discrete logarithms that Shor's algorithm would solve efficiently. This creates a harvest now, decrypt later risk for the data that must remain confidential for years. By contrast, the quantum communication and especially QKD derives security from physical law. Unknown quantum state cannot be cloned and incompatible measurements disturb them, so interception is inherently detectable. The strongest strategy is combined here: deploy post quantum cryptography PQC for broad software based protection, and use QKD where sites can share optical to supply tamper evident keys with a long horizon confidentiality. Practically, organizations should inventory long lived data, pilot QKD and high value links, and integrate both QKD and PQC in existing PKI KMS so that the security stack remains resilient throughout the quantum era. And speaking of quantum networks, the quantum networks interconnect spatially separated quantum devices so they can share entanglement and exchange quantum information very securely. At a physical layer, photonic links distribute entanglement between nodes equipped with source, quantum memories for storage, and eventually repeaters that extend range via entangled swapping. A classical control plane handles synchronization, routing, shifting, and error correlation, while keys or teleported states ride on quantum channels. Beyond QKD, such network-enabled distributed quantum computing combines small processors into a large virtual machine, and network sensing include ultra precise time transfer and clone synchronization. In short, quantum networks are the backbone of the future quantum internet. Unify secure communication and cooperative computing and metrology. Securing, as we talk today, tomorrow, quantum key distribution offers, as I told, information theoretic confidentiality. Under standard authenticated conditions, uniform quantum states cannot be cloned and incompatible measurements disturb them. So, passive interception fails and active probing is revealed by an elevated qubit during the test phase. Practically, QKD supplies fresh, tamper evident keys to conventional encryptors, providing durable protection against harvest now, decrypt later threats. The prudent path is hybrid, as I told. Deploy QQAD on high valued links and post quantum cryptography broadly. Integrate both with the existing PKI KMS and align pilots with emerging standards. While satellites, metro fiber testbeds, and integrated photonic maturing quantum secure networking is no longer speculative, it is near term compatible. We can adapt responsibly today. Speaking of India's progress in quantum communication, India's program spans free space, fiber, and satellite QKD. In terms of free space, in June 2025, IIT Delhi and DRDO demonstrated entanglement based QKD over almost an approximate 1 kilometer open air, achieving approximately around 240 bits per second secure key rate with QBR less than 7%. And speaking of fiber links, in 2022, DRDO and IIT Delhi realized an intercity QKD link of less than 100 kilometers between Vidyanchal and Prayagraj on standard telecom fiber. By 2024, entanglement-based QKD was extended to 100 km in optical fiber with 50-kilometer lab and 8-kilometer field trials. And speaking of satellite-based quantum communication, RRI and ISRO are co-developing satellite QKD, building on free space trials and adaptive optics. A QKD-enabled satellite, which is a SAQTI, is targeted for 2025-26, enabling long-distance nation scale secure links. And continuing in terms of research and development, mm, India's program is coordinating well funded. National Quantum Mission from 2023 to 2031 builds four hubs: computing, communication, sensing, and metrology and material devices to deliver test beds, talent, and standards. QNU Labs to India's first communications cyber security firms uh, with fielded QKD products for banks and defense. Also, Quest 2019 DST backs R&D in uh, quantum cryptography and communication across academia and startups. Um, Also, in defense, as I mentioned, DRDO is developing quantum resilient cryptography and running field trials with the Army's Northern Command. Uh, International ties include partnership with ES, with Europe, United States, and Japan. Advanced research and secure satellite links. ISRO leads satellite QKD and NAVIC linked experiments. GOI DST in space provided policy funding the deployment support. Basically, the outcome would be a national quantum secure backbone targeted by 2031 for cyber security, defense, banking, uh, which I already mentioned these slides, and satellite communication. On the conclusion, I would like to say quantum communication pairs quantum key distribution and entanglement to deliver tamper evident long horizon confidentiality forming the secure, sustainable, or for a future quantum internet. If it completes post quantum cryptography, supply physics backed keys and conventional encryptors for layer defense, the road ahead is very clear. Overcome loss and decoherence, mature quantum memories repeaters, reduce cost through integrated photonic and device standards for interpretability. For India and the world, this is both strategic necessity and time opportunity to build resilient at scale quantum secure networks. That's all from my end. Thank you very much, guys. Everyone, thanks for your very patient listening, for all the educated and valuable audience. Thank you. Over to you. Uh, Over to you, Sneha.
Thank you, sir. The next session will start from 7:30.
Okay. Thank you, everyone.
Participant kindly fill the attendance and feedback form. Due to the network issue, the session will start from 7:30. few people are still not filled the feedback form, kindly fill the feedback form, and the next section will start from 7:20 p.m. Kindly log in. Kindly fill the feedback form as soon as possible. After 5 minutes, the session will start. Participants kindly join as soon as possible. Further, it gives me an immense pleasure to introduce our distinguished resource person for today's second session on quantum technology. We have with us Dr. S. Sampath Kumar, Associate Professor from Department of Computer Science and Engineering at Sri Ishwar College of Engineering, Coimbatore. Dr. Sampath Kumar sir brings with him an impressive 14 plus year of academic experience and holds a PhD in Information and Communication Engineering from Anna University. His research proves its evident through his 21 published papers, including contributions to SSCI and SOOPS index journals and 4 published patents covering cutting-edge technologies. What makes Dr. Sampath Kumar particularly relevant to our FTP in his diverse research interests spanning theory of computation, blockchain, Gen AI, and cloud computing, all of which interacts beautifully with quantum technologies. Its practical expertise extends to bring a DGCA certified remote pilot training instructor, showcasing its commitment to emerging technologies. As an innovation ambassador at his institution, he has mentored multiple Smart India hackathon winning teams and has been recognized with the Best Mentor Award for 3 consecutive years. His dedications to nurturing innovations and his extensive experience with advanced computational paradigms make him the perfect guide for our explosion into quantum technologies today. Please join me in extending a warm welcome to Dr. S. Sampath Kumar sir. Sir, the session is yours. Thank you.
Ma'am, am I audible? Hello?
Yes, sir, you're audible.
Okay. Thank you. Thanks for the introduction, ma'am. So, my dear faculty members, myself is Dr. Sampath Kumar. And I'm going to handle quantum key distribution and cryptography topic for you for the next 1.5 hours. And this is going to be agenda of my presentation. So I'm going to, I have split my speech into 4 parts. First part of presentation, I'm going to tell you about what is the foundation of quantum cryptography and what is the need for quantum cryptography and what is the problem with classical cryptography and why we need to move for quantum cryptography. That is going to be my first part of presentation. Followed by that, I'm going to tell you about the quantum key distribution protocols. So there are quite some popular quantum key distribution protocols are there. And I'm going to give a short introduction about a few popular protocols. And in the third part, I'm going to tell you about tell you about security analysis, practical application, and challenges of quantum cryptography. And followed by that, in the last part of my presentation, I'm going to tell you about the future of quantum, post-quantum future and the post-quantum cryptography. Hope my voice is audible. If my voice is not audible, please let me know. And for the past 2 days, I think all the faculty members would have get an idea about what is quantum computing. And today we are going to discuss about quantum key distribution. And the quantum key distribution is a fancy way of saying we finally found a way to send a secrets where even the noisiest student with the best Wi-Fi can't improve. And in the classical cryptography, hackers can listen in without knowing, which means if you send a data to a target person, if a person A is sending some data to person B, and without knowing, without person A or person B knows, a hacker can easily take the data. Whereas in quantum cryptography, if anyone tries to spy, if even just try to spy, okay, we will know immediately. And it is the first technology in the history of human being where we can we can say with the confidence that caught you hacker. And so, Buckler faculty members, today we'll learn how quantum computers break the things and quantum cryptography fix the things, and hopefully we won't break our brains in the process. Okay. So first of all, what is the need for learning quantum computing? So this year 2025. 2025 is a very remarkable year in the history of human being because United Nations has designated year 2025 as a year of quantum science and technology to mark 100 years of quantum mechanics and spotlight its transformative impact. And a series of global events like this will showcase how quantum technologies are revolutionizing secure communication, advanced computing, and ultra precise sensing and metrology. And as the world stepped into the era of second quantum revolution or quantum 2.0, the quantum 2.0, which is the breakthrough in the quantum computing, cryptography, and communication. And this is poised to reshape the industry and tackle the critical global challenges. And amid the shifting geopolitical dynamics, digital dominance has become the strategic priority. And the nations leading in quantum technologies are expected to gain a decisive edge. And global powers are investing heavily, global powers are investing heavily to stay ahead in the innovation race. And according to Quetshaw, worldwide investment in quantum science and technology has already surpassed 55 billions. And with China alone has contributing around $15 billion. Okay, you see, around 1/4 of investment is coming only from China. I hope my voice is audible. And and according to McKinsey and the company's 2023 quantum technology monitor report, this projects that the market will reach $106 billion by 2040, and I think by year 2030 itself, the quantum market will reach at least $150 billion, according to my expectation. And quantum science is said to unlock new frontiers, redefining innovation, and placing itself at the core of next technological revolution. And if you see this map showcases which are all countries which has invested in quantum related research and development. You see, we can take. I'm not going to bother much about other countries. If we take India, we already started to research about quantum computing. So Indian government has spent has allocated around 600 crore rupees in I think in 2023 2024 budget. I think 2024 budget they have allocated around 600,000 rupees, which is around $720 million, which is a huge money for a budding quantum industry and budding quantum researchers in India. And, and these are all the four verticals of quantum technology. Four verticals of quantum technology. So quantum computing, quantum communication, quantum materials and devices, quantum sensing and metrology. These are all the four verticals of quantum technology. And I think in the session 5, the resource person would have discussed about quantum communication. So I'm going to discuss about quantum key distribution, which is a part of quantum communication vertical. And when I started to learn about quantum computing, it's like entering into a dark forest with my eyes tied. Okay, for nearly first week. Okay, I literally don't understand anything in quantum computing. Literally, I don't understand in quantum computing. Then I started to discuss with my friend Dr. Mohan, who is a veteran in quantum computing research, and he opened many new dimension of thinking. And to be frank, you need an extra brain to understand quantum computing. Okay, I'm not saying that it is difficult, because it is actually difficult to understand quantum computing. And for the next 1.5 hours, I'm going to make it as simple as possible to share my knowledge in quantum key distribution. So I have not prepared any fancy simulation. I have not. I prepared a simulation and a very lengthy program to simulate an algorithm, and it will take at least 3 to 4 hours to explain only about the program, and it will take another 1 or 2 hours to explain about what is happening in the algorithm. So I think it will take at least 5 hours for me to explain everything. So the time allocated for me is 1.5 hours. So in the limited time, so what I thought is, instead of sharing everything in detail, why can't I share the knowledge about quantum key distribution in as simple language as possible. So that's what I'm going to do for the next 1.5 hours. So we're going to step into the first part of my presentation. So foundation of quantum cryptography. So all of you would have a doubt that we already have a sophisticated cryptographic algorithms are there, like RSA, ECC, and we are using these algorithms. We are using these cryptographic algorithms for securing our day-to-day communication. It may be not only day-to-day communication; it also used for securing online banking and emails. Okay, whatever emails we are sending, it is used for securing all those things. Even if you take WhatsApp. WhatsApp encryption, even in WhatsApp encryption, then using such kind of sophisticated algorithm to secure the communication. We already have a sophisticated cryptography algorithm for securing and communication. What is the need for going for cryptographic quantum cryptography? The thing is, my dear friends, uh, when it comes to the classical cryptographic algorithm, like RSA ECC, yes, it is a classical algorithm only. We can claim that right now I'm using RSA and ECC. How can I tell that it is a classical algorithm? Because when it comes to quantum computing, whatever whatever algorithm we are using, we are using this just a small pinch, okay, small pinch of computing, okay. The quantum computer can break these algorithm in a matter of seconds, maybe in a matter of minutes, okay. Some algorithm can be cracked within a matter of seconds, okay, because all these algorithms are depending on fact that some mathematical problem, like factoring a big number, or very hard for which is very hard for classical computers. Okay, which is if you take a factoring of uh, 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 prime numbers. Okay, it will take a huge amount of time for us to crack this uh, factoring of prime numbers for classical computing. Classical computer doesn't the computer which you are using, von Neumann based computer, or Alan Turing's concept based computers. Okay, all these computers are based on the mathematical problems only. These mathematical problems can be solved within a matter of minutes. Okay, and when it comes to quantum computer, okay, we are not fully developed the quantum computer, but when we develop the quantum computer which can run source algorithm, okay, the source algorithm, I'll explain about source algorithm later. And if you use a source algorithm, and this source algorithm can factor a big number much faster. Okay, this means RSA, ECC, and similar systems could be broken, exposing encrypted data. And government and companies are already worried about an attack called as harvest now and decrypt data, where in which the hackers will collect the data which is sent through the internet. Okay, they'll use some sophisticated programs. They will inject this program in a router. Already, there is a suspicion that one popular country, okay, which is trying to gain digital dominance, is already doing this. That's why Indian government wants to develop all the digital devices ingeniously. Uh, and what they do is they'll collect all the data and they'll store all those data in their homeland. And this data may not be a useful one right now, but maybe why? Because if they try to decrypt the data right now, it will take a huge amount of time to decrypt the data. Maybe it will take days, or it may take years, or it may take a decade, or more than a century to decode the data. But once we got what is that quantum computer in our hand, we can easily crack this the classical algorithm, classical encrypted data in a matter of minutes. So governments are afraid of this harvest now and decrypt later attack. And as I told you already, quantum computing is going to change the digital landscape forever. So why this is possible? Because of many reasons. One such reason is source algorithm. So source algorithm says that imagine if you take a quantum, if you take a classical algorithm like RSA, and in that what you're going to do is imagine you're going to you have given a chain number, say one with hundreds of digits, and asked to find prime numbers, two prime numbers, where two prime numbers to which will be multiplied to get that number. Okay, and this is called as a factoring problem, or a prime factoring problem, and it is the backbone of classical cryptography like RSA. And RSA encryption works because factoring huge numbers is really hard for a classical computer, and it could take centuries, decade, or even a centuries to crack this key by using a brute force method. Whereas if you take a source algorithm, which is implemented in a quantum computing, a source algorithm is a quantum algorithm that can factor a large numbers exponentially faster, and they also know the class exponentially faster than any known classical method, and it uses quantum the power of quantum mechanics like superposition and interference to find the patterns that classical computers would miss. And what happens is in classical computer when it tries to crack a key, it will classical computer will try one key at a time, and it will take as I told you already, it will take a decade, or maybe a century to unlock to find the key. Whereas in quantum technology with source algorithm, what happens is this is where source algorithm and the quantum computing gets interested. What happens is it will try all the possible keys at the same time. Okay, parallelly it will try. Okay, and this is an unbelievable amount of computation which right now we don't have, but in future maybe within a decade, or after a decade we would have with the quantum 3.0. During that time we could have an actual quantum computer. At that time, these classical algorithms can be cracked within a matter of minutes. Okay, why it is a big deal? You can ask me why it is a big deal. So, what is going to affect me? What is going to what is the problem for me? Okay, the problem is if a large scale quantum computers became practical, source algorithm could break RSA encryption. Literally, it can break RSA encryption within a matter of minutes. Okay, and the RSA algorithm secures everything from banking transaction to email. So, so you could have imagine the chaos and confusion which will happen if this RSA encryption can be breakable and breakable in a matter of minutes or matter of seconds or matter of whatever it is. Okay, and that's why the researchers are racing to build a quantum safe cryptography. Okay, so this is the reason why researchers are moving to find quantum safe cryptography, and we are going to use quantum principles for building a quantum secure cryptography. So we are going to use four main properties of quantum mechanics. And the first one is called as a no-clone theorem. The second one is called as measurement disturbance. And the third one is called as superposition. And the fourth one is called as an entanglement. And we'll discuss each in detail. So what is no-clone theorem? So I think in last session itself, resource person would brief about no-clone theorem. So I'm going to repeat it again. So what this no-clone theorem says is I can put like this. No code in quantum cryptography shift the foundation of security from hard to solve to practically impossible to break. It's like locking your door, not with a key, but with the law of nature. Okay, so instead of using the traditional key, you'll use photons to encrypt your data, so that it will be impossible for a hacker to hack this. And this is called as a no-clone theorem. And this makes sure that Heisenberg's uncertainty principle in action. And to be frank, these are all not some magics or some clever tricks. Okay, this is the actual computer or actual concept which is built into the fabric of reality. And when it comes to Heisenberg's uncertainty principle, again it says that we cannot precisely know the position of a and the momentum of a particle at the same time. Let me put it like this. If you take just have a look at these two pictures, okay? Quantum blur. Just imagine that you're going to take a photograph of a hummingbird in flight. So if you want to take a photograph of a hummingbird, you got two options. Okay, one is you can adjust the shutter speed of shutter, so that the shutter will close very fastly to freeze its position. And when it freezes the position, you'll lose the blur. If you take the left hand side image, okay, you can clearly you can clearly see the wings of hummingbird, but you cannot see how fast it is moving. Okay, this is what happens if you close the shutter very fast, and if you take the right hand side. So what is happening is you can see that the wings of hummingbirds is moving very fast. So the wings became blurry. So you lose the exact position of it. Okay. So what is happening is you can capture only one thing at a time. Either you can capture the position or a momentum, not both at the time. So quantum particles behave like this hummingbird. And to be frank, this quantum particles will behave more mysteriously, and if you approach these quantum particles with whatever knowledge you have about classical physics or classical computing or classical physics, if you try to understand this quantum particles with the classical physics and classical physics, I'm sure that you will end up in a more confusing state. Okay. It's like to put it in other words, it's like learning a new programming language. When you're trying to learn a new programming language, you should forget whatever you learned already. Okay, only if you approach the new programming language like a clean slate, you can able to understand what they say, or else you'll try to understand the new concept with an existing concept, which will be a big trouble for. Okay. So next is measurement of distribution. So what it means in quantum mechanics, so you can't observe quantum particle without changing it. So if this is the direct consequence of Heisenberg's uncertainty principle, and what it means in cryptography. So in quantum key distribution or QKD, if an eavesdropper tries to intercept and measure the photons being exchanged between two parties, say the traditional example Alice and Bob, she disturbed their quantum state. Okay, this disturbance introduced detectable errors in the key, alerting Alice and Bob. Let me put it in this way: think of a fragile wax on a letter. I think we already know about this fragile wax. I think there is something called as arak. I think in Kannada also the same word. I think there's a wax called as arak, and that will be put on a letter. If we pour that on a letter, and if we keep a stamp on it, if we keep a seal on it, if someone tries to open the seal, if someone tries to open the letter, the seal will break. Okay, obviously the seal will break. So when you look at the letter, you will come to a conclusion that someone has already tampered the letter. So this is what happened in measurement of distribution. Sorry, measurement of disturbance. So two party will be involved, and the data transmission will be taking place between two parties. If someone tries to eavesdrops into the communication, obviously there will be some disturbance in the photons. And with this disturbance, both the party will come to a conclusion that someone has already tries to eavesdrops into the communication. So they will change the key and they will exchange the information again. Okay. And the next is superposition. What it means is quantum particles like photons and electrons can exist in multiple states simultaneously. Yes, it is possible. Yes, it is possible that the photons and electrons will exist in multiple states simultaneously, and this will exist in multiple states simultaneously until someone measures it. If someone tries to measure it, their multiple existence will be disturbed, and this is called as a superposition. And how it is going to impact in cryptography. And what happens in QKD is photons can be encoded in a superposed states like horizontal and vertical polarization. If Eve tries to measure them, superposition will collapse into a definite state, revealing the hacker's presence. And let me put it this way: think of spinning a coin. It is both head and tail when it starts to spin. But once you catch the coin, it is either head or tail. Okay, so what happens is if you try to measure the collapsing, measure what is happening, measure what is happening, obviously it will collapse the possibilities. So once the possibilities collapsed, you'll come to a conclusion that someone has intruded the communication. And the next is quantum entanglement. This is a very, very, very interesting interesting theory where actually I started to learn about quantum computing only after learning about quantum entanglement. That's another story and tell on another day. So what it means is there'll be two quantum particles that will be entangled, meaning their states are linked. Changing one particle will instantly affect the other particle, even if it is light years. So, so what I told you maybe hard to imagine. But if you look at the if you have a habit of watching Indian movies, Indian classic movies, you will not be surprised with what I say. So there'll be a twins in twins, and those twins will be separated due to some unimaginable things happening in their family. When you pinch one twin, the other twin will feel the pain. Okay, you can you can imagine like that, and how it is going to impact with cryptography. You see the protocols like ECART 91 uses entangled particles for distribution. If a hacker tries to tamper with one particle, the correlation between the entangled pair is broken, which alerts the sender and receiver. So let me put this in a simple words. Imagine you got two dice which is magically linked. If one rolls to 6, the other must roll to 6 too. Okay. If one dice is rolled to 6 and the other will also roll to 6. Okay. If someone interferes or break into the link, the dice will no longer matches, revealing the intrusion. Okay. And this is the principle and cryptographic behavior of four concepts which I discovered, which I told you. No cloning is quantum state cannot be precisely copied. No cloning theorem. The quantum behavior of no cloning theorem will be quantum states cannot be perfectly copied, and when it comes to measurable disturbance, measuring a state, measuring will change the state of particles, and superposition is particle will exist in multiple state at once. And when it comes to entanglement, particles are linked and share the instant correction. Linked particle will share the instant correction. And this is the historical context of evolution. The quantum the research of quantum computing starts in 1970s. The famous scientist called Stephen Weissner in the 1970s researched. He is a physicist who first suggested using quantum mechanics for information security. He's the very first physicist who suggested this technique. And he proposes two important concepts. One is quantum money, and the other one is quantum conjugate coding. The quantum money is a concept in which it says that you have to prepare a banknote with a quantum state that cannot be copied because of no cloning theorem. And and if you imagine a Bitcoin, maybe Bitcoin may be based on quantum money, but it's not completely based on quantum money. That's a different topic. And the next one is quantum conjugate coding, where you will be encoding messages using quantum states that are not simultaneously measurable, folding which is the foundation of quantum cryptography. And his work planted the idea of quantum cryptography. Okay. He is the first one to propose that quantum mechanics can be used for what's that information security, and he is the first one to propose a revolutionary concept. And later in 1984, starting off 1980s, and exactly in year 1984, two scientists, namely Charles Bennett and Gilles Bresson, introduced a protocol called as BB84. In 1984, they introduced a protocol called as BB84. It is the first practical protocol for quantum key distribution. Until that, when someone speaks about quantum key distribution, most of the scientific community will tell that he's bluffing something nonsense. So these two scientists make this bluffing possible, convert this bluffing into reality. They uses polarized protons to generate secret key between two parties. So there will be two parties will be there, and they use photons to create polarized photons between for sharing secret keys. And when you tries to eavesdrop into the photons, obviously the polarization of photons will be changed, and something will happen. And the key ideas, key ideas, any eavesdropping disturbs the quantum state, and which can be detected and which ensures the security. This was the starting point of modern quantum cryptography, and it is still widely studied today. And the next measurable research is by in next measurable research was released in sorry, not measurable research. It's revolutionary research was introduced in 1991 with the name ECAR protocol or E91 protocol, which is very famously called as E91. This used quantum entanglement for security key distribution, and this is linked to cryptography with Bell's theorem. I'll tell about Bell's theorem in the later part of my presentation. And the commercial QKD system became possible in 2000s, and the first QKD network was developed by none other than DARPA Quantum Network in SEC, I think QC project. I think I'm not sure about the project, but I'm damn sure that it is by none other than DARPA Quantum Network. I think SEC QC or SEC OQC. I'm not sure about the project name. In that project only, they have introduced QKD. Okay, and today in hybrid security, hybrid security, we have started to develop post quantum cryptography, which is called as PQC, plus practical QKD over fiber and satellites. And recently, China has developed a satellite called as Maisius satellite, in which they used QKD. And what happens is in 1970s to 80s, quantum cryptography started as a theoretical idea and became a practical idea when Bennett and Bassad introduces BB84 protocol in 1984. And today there are two parallel paths available for us. One is PQC, post-quantum cryptography, which is a software based and which is easy to deploy. Projects data against which products data against quantum computers. And this uses a mathematical concepts which even quantum computers will find hard to break. And the other one is you got the QC, okay, quantum computing, which uses physical computers. Physical quantum computers are built and which provides ultimate security, but harder to implement. Okay, the thing is, PQC is easy to deploy because it is software based, and when it comes to QC, quantum computing, it is purely hardware based, but it is hard to implement. And this is the historical evolution of this is the evolution of post-quantum cryptography and quantum cryptography. When it comes to basis, post-quantum cryptography uses a hard mathematical problem, which is quantum safe. Even a quantum computer find it very hard to break this post-quantum cryptography based algorithms. And when it comes to quantum cryptography, it uses law of quantum physics. Obviously, you'll design some what is that physical hardware, physical or quantum hardware to implement quantum cryptography. What happens in PQC is it will run on classical computers, so it's itself and it is easy to deploy. But when it comes to quantum cryptography, you need quantum channels and detectors for implementing this. And quantum post-quantum cryptography is lattice-based crypto, and it is hash-based signature. Whereas when it comes to quantum cryptography, it uses BB84, E91, and QKD based algorithms. This is when it comes to PQC. PQC is believed to be quantum resistance. It is believed. Let me make it clear. It is believed, but it is not true. Okay. Whereas when it comes to quantum cryptography, it is information. Information is theoretically secure. Information is theoretically secure, and it is provably secure. Okay, so when it comes to you got an imaginary concept in which you are claiming that everything is safe, but it is not proven. On the other hand, you got something which is hard to build, but it will give you an assurance that it is secure. So that's why we are moving to quantum cryptography in a faster phase. And when it comes to cost for building a post quantum cryptography, it is very high. The cost of building this quantum post quantum cost of building a quantum cryptography machine is higher because it requires a specialized hardware for implementing all these things. The hardware is right now we are trying to build the hardware. We have almost achieved. We have almost designed the hardware, but still we need more R&D to make it commercial. Okay. And when it comes to post quantum cryptography, the cost for building this post quantum cryptography based algorithm is the system is low, and this requires only a software upgrade and nothing else. And use cases. This is the when it comes to post quantum cryptography, it is a long term replacement for RSA and the ECC. And when it comes to quantum cryptography, this is an ultimate secure key exchange for high value communication. So what is like post quantum cryptography is it's like my left eye, and quantum cryptography is my right eye. So I cannot claim that my left eye is better than right eye, or my right eye is better than my left eye. So both are equally important, and both need to be researched equally. So I'm not going to judge that PQC is better than QC or QC is better than PQC. Both are okay. We are forced to study both the things. And these are all the basic concepts. When it comes to classical cryptography, uh, the security relies on mathematical models. Example for classical cryptography, we purely rely on mathematical problem, which is hard for classical computers to break it. When it comes to quantum cryptography, it purely relies on law of physics. And when it comes to vulnerability, a classical cryptography can be easily break using a source algorithm or a Brewer's algorithm. Both are future risk. Both are future risk, and we are imagining that when we obtain when we design the quantum computer, these classical cryptography can be made within a matter of minutes. So that's why you're afraid. That's why you're moving to quantum cryptography, and we are claiming that this cannot be broken or detectable, or which cannot be broken or detectable. And when it comes to key distribution, classical cryptography is done using PKI, a concept called as PKI, public key infrastructure. And when it comes to quantum cryptography, it is done using QKD, quantum key distribution. And when it comes to eavesdropping detection, in classical cryptography, unfortunately, we don't have a direct method to detect if someone is intercepting our message. I can't claim that you're using some XYZ method or by using ABC method, I can easily detect what is if someone tries to intercept my message. I can easily detect. But when it comes to the practical part of detecting those interception, it is somewhat hard. Okay, we should accept that it is hard. But when it comes to quantum cryptography, even if someone think to eavesdrop into our quantum message, we can easily deal with it. Okay, and implementation of classical cryptography is purely based on software, and which is very easy to scale. And when it comes to quantum cryptography, it need a special quantum channels, either a fiber optic or a satellite, and detectors for doing all these things. And, these are all the four concepts for quantum phenomena for security. One is superposition. It says about the quantum particles like a photon, which can exist in multiple states, which is horizontal and vertical position simultaneously. And security, when it comes to security benefit of a superposition, this allows random key generation in multiple bases. And when it comes to eavesdroppers, if eavesdroppers measures this, they will obviously get into a wrong result. And the next one is measurement disturbance. And what happens is if an eavesdroppers try to measure what is happening in communication, like, the state of the state will collapse, and obviously the sender and receiver will come to a conclusion that someone has intercepted the message. And next one is no cloning theorem, which says that it is impossible to create an exact copy of an unknown quantum state. Only if you know the quantum state, you can create a copy. But when you try to know the state, the measurement of disturbance will come to action, and if you try to measure, obviously the communication will collapse. The next one is the entanglement, where two particles are entangles. So two entangled particles share a same state, and no matter the distance. Literally, it says that even if there is light years apart between the two particles will share the same state. So security benefit for quantum entanglement is if someone tries to tamper one particle, obviously it will reflect in the other particle, so that we can easily detect what is happening to the other particle. Okay. Okay, now we are moving to the second part of presentation. My second part of presentation is about the quantum key distribution protocols. There are a handful of key distribution protocols. One such protocol is BB84 protocol. So what happens is there'll be two parties will be there, Alice and Bob. Alice and Bob will try to communicate. But the voice is clear now. Whether I'm audible? Can someone drop a
Yes, sir,
message
you're
whether
audible,
I'm
sir.
audible? Okay, ma'am. I hope I'm not boring. Okay, thank you, Shanmugam, sir. So what this protocols what this protocols is let me put this protocol in a simpler term, because uh, again a historical view about this protocol. It took nearly 1 week for me to understand what is happening. There is a particle which there'll be some few particles will be there, and uh, why? Because I try to understand this protocol with a classical physics sense. When I try to understand this with a classical physics sense, nothing makes sense. Okay. On fine day, what I did is I make sure that I will not. I promise myself that I will not recollect any classical physics concept. I will not recall any classical physics concept, and And after that, I try to understand this BB84 protocol. After that, it makes sense. Okay. So what I'm going to do is I'm going to explain you all about this BB84 protocol in a simpler manner. So what is happening is there'll be two parties will be there. So let us call them as Alice and Bob. So two parties will be there, and these two parties will share some information over a classical channel. Okay, classical channel. It may be wired connection or some wireless connection. Okay. So what Alice does is Alice will prepare photons with some random bits, say obviously 0 and 1, and some random bases, either plus or x. Okay. So this is plus, okay, horizontal and vertical. We will call it as a HV basis. The other one is called as DA basis. Okay, diagonal basis. And this is a photon source. And what happens after that is she will try to send this photons to Bob over a communication channel. And after at the receiver end, okay, at the receiver end, Bob will use a detector to receive the communication, and Bob will try to measure each photon with a random base. Okay. After that, what happens is then Alice and Bob will publicly compare this bases. Okay, they compare only the base, not the bits. Okay, they'll compare only the base, not the bits, and keeping only these bits where bases match. Okay, you can look at the diagram. Okay, you can look at the diagram. Okay, Alice is sharing this base. Okay, Bob is guessing this base. So these two matches. Okay, this is horizontal. This is HV base. So this base is correct. Bob guesses this base correctly. So they will keep it. Next is Alice is sending a diagonal base. Bob guessed it wrongly. So Bob will discard this base. So likewise, they will try to likewise Bob will guess all the base and they will come back. Okay. So what happens after that is obviously there'll be some corrections will be there. After this, they will take the key and they will sacrifice a few bits to check whether there is error, whether there is any error in the whether there is any error in the data. Okay. If the error is within a small range, say there'll be a threshold value will be there. The error is within say 5% or 10% for namesake. If it is in threshold range, they will trust the remaining bits and use them as a secret key. If there is any major corrections is there, obviously Bob and Alice will come to a conclusion that someone has tampered this communication, and because of the tampering, the base of the photons has changed. And what happens is eavesdropping detection. We'll call it as a QBER. This eavesdropping detection is easy to detect. I hope no one would have understood what I said. This is what happens to me when I started to learn about BB84 protocol. So let me put in a simple way. So think of Alice and Bob is passing some information. Say they are passing some colored breads through a pipe. Okay, Alice is Alice is randomly choosing color bread, say a red color bread and a blue color bread, and there'll be two shapes for the bread. One is a round bread, the other one is a square bread. And please remember, they are sending this bread through a pipeline. And Bob guesses the shape, and the receiver and at the receiver end, Bob will tries to guess the shape when picking the bread. Okay. Later, they will compare the shape choices publicly, and they will keep only the breads where shapes match. Okay. So what happens is if a thief like a hacker, so we can assume like a hacker, tries to grab the bread. Obviously, there will be some scratches in the bread. So by mistake, he or she will make some scratches in the bread. And Alice and Bob will notice the scratches, which in our case we'll call it as an error, and they will throw the entire set. So they will come to a conclusion that someone has intercepted this message, someone has intercepted this bread message, and we should discard it. So whatever I told you, I have explained this again. So this is what happens in DB84 protocol. The next protocol is E91 protocol, or this is an entanglement based protocol. The core idea is about entanglement and Bell's inequalities. And what happens in this protocol is we uses quantum entanglement, which is a spooky connection between particles to generate secure keys. Unlike BB84, where Alice sends some protons to Bob. Here, nothing is exchanged. Unlike BB84, here source creates an entangled photon pair and distributes one to Alice and the other one to Bob. Okay, so there'll be a set of protons will be there. So both the protons is going to behave same. Bob is going to hold one proton and Alice is going to hold another proton. Okay. So what happens? What happens in quantum entanglement is two particles can be created in such a way that properties are correlated, and this is measurable one. And the other, if you measure one, the other's result is instantly determined. Okay, if you have a proton with some polarity, okay, other proton will have the same polarity, no matter what is the results. Okay, that they may be placed light years away, but both the protons will behave similarly. Okay, and what's Bell's inequality? What happens in Bell's inequality? And the Bell's inequality is a mathematical test to distinguish this quantum entanglement from hidden variable, which is a classical variable correction. If Alice and Bob's measurement results, Alice and Bob's measurement results violates Bell's inequality, they know they share two quantum entanglement. Okay, if there is any inequality, then they will come to a conclusion that they will share a two quantum entanglement. And when it comes to security, what is security is? Because one can secretly reciprocate or false this correction. Any eavesdropping attempt to break this correlation can be easily done. So this is the security part of this E91 protocol. So next we got BBM 92 protocol, which is again an entanglement based protocol. This is similar to E91. These protocol also used quantum entanglement, and this unlike E91, sorry, BB8 protocol. No, there will not be any proton preparation step will be there. It also uses the quantum photon pair. It also uses entangled photon pairs, but there is no photon preparation step will be there. Okay, and there will not be any explicit Bell test is involved. Just we use a matching basis result to form a cake. So when it comes to simplicity, BBM 92 protocol is somewhat simpler when it comes to when it gets compared with the E91. And the next protocol is next one is continuous variable CVQKV. This is the traditional QKD protocols like BB84 uses a single photons and the discrete values. Okay, discrete values it should either they use 0 or 1. When it comes to CVQKD, what happens is it uses continuous properties of light. Okay, it uses continuous properties of light. Okay, and in a traditional QKD protocol, we rely on some sophisticated protocol based methods. Whereas in CVQKD, we are relying on some tech which is already in exist. Okay. So what happens in CVQKD? They are relying on continuous properties of light. Specifically, to be more specific, they rely on amplitude and phase of an electromagnetic field, which is called as quadrature. I think quadrature to encode key information instead of thinking in terms of uh, photon clicks. We are thinking in terms of measuring tiny fluctuations in the laser beam. If there is any tiny fluctuations in the laser beam, we'll come to a conclusion that someone has stamped our message. So key differences, instead of sending a single fragile photons one by one, Alice uses a bright continuous laser beam for sending the secret information. Sending the secret information to Bob. And next we are moving to the third. Next we are moving to the third part of my presentation. It's about security analysis, practical application, and challenges of QKD. Okay. So when it comes to security analysis, just a moment. So, so the mathematical foundation for security. So obviously the security, the classical security is based on mathematical foundation, and the quantum key distribution security is not based on computational hardness. Computational hardness in the sense it is not based on factoring prime numbers. It is based on law of physics and no cloning theorem, obviously. And since we are using this, we cannot make a perfect copy of an unknown quantum state. Only if you know the state of a state of quantum, what is happening in photons and all those things, you can make a perfect copy. And if you try to make a perfect copy of photon or a quantum state, it will tamper the state of quantum. So when you observe that when it reaches the destination, the receiver will come to a conclusion that since the state of photons has changed, the receiver will come to a conclusion that someone has tampered the message. Okay. Let me put it in a more simpler terms, like say you are trying to take a photocopy of a snowflake. What happens? The copy melts during the attempt. Obviously, you cannot make a photocopy of a snowflake. Just a minute. Okay. So what happens in an attack? Say if someone is trying to intercept and resend the data. So what happens in QKD? if you try to measure the photons and resend the gases, okay, it will introduce the error. Okay, it will introduce errors in the communication. The possible differences we can go for Kuber reduction. Kuber means quantum bit error rate detection. This is the difference we can do it. The next possible attacks is photon number splitting, which is called as PNS. So this is another research, a big research area for photon number splitting. What happens is if Eve try to steal one photon from a Eve will try to steal one photon from a multi-photon pulse. Okay, well, this is quantum entanglement related problem. We can use BB84. We can use BB84 decoy state BB84 for a difference where Alice will randomly vary its pulse intensities. The next possible attack is side channel attack. Again, what happens in side channel attacks is exploit. The hacker will try to exploit the imperfection like detectors, timing loop. They'll try to exploit all these things and what we can do is, again, this is a very big research area. What we can do is we can we can use a device independent QKD, which is for a better hardware shielding can be done. Okay. And where it is actually implemented, and what are the use cases of QKD? The commercial QKD system is available in fiber optic satellite communication and some chip-based implementation. So fiber-based QKD is, I think, it is deployed in China between Beijing and Shanghai. I think the distance between these two cities is more than 1,500. No, it will be more than 2,000 kilometers will be there. Fiber-based QKD is implemented between these two cities, and next is it is also QKD is also implemented in satellites. Again, China's Vicious satellite is demonstrated global QKD against China. The next one is chip-based implementation. This integrate photonics research. Integrated photonics research is creating portable cost-effective system. Okay, this is intended to create a portable cost-effective chip-based QKD system. Again, I don't want to repeat again. China again has an upper hand in this research also, since you see they have spent billions and billions of dollars in quantum research. So obviously, they have some upper hand right now in quantum research. And key uses of this QKD is we can use it in government and defense sector application. Maybe the government sectors may use it for diplomatic communication between two countries. And it can be used in military communication, military command security. So say suppose from one end of Indian border to other end of Indian border, say from eastern end of Indian border, we have to send some secure military communication to the western end of Indian border. So we can use this QKD for sending the secure communication, sending secure data. And we can use it in banking and finance. So as I told you already, the classical cryptographic algorithms will not stand before QKD based quantum will not stand before quantum cryptography, quantum computing machines. So we are forced to change our traditional cryptographic algorithms. So these traditional cryptographic algorithms can be replaced using QKD based security, and we can use this QKD based system in critical infrastructure like power grid communication, or a water treatment plant, or in a medical related infrastructure, or some atomic power plants. We can use this QKD in such critical infrastructure, and also we can use it in cloud and telecoms, like to send the secure data between two centers, two interconnected centers. We can also use that. And what is the current limitation and open challenges? Okay, there are these are all challenges right now we are facing in QKD. One is distance limitations. Okay, right now. Okay, photons can if you try to send photons over fiber, if the distance is more than 100 to 200 kilometers, if you try to send photons over a fiber without repeaters, okay, there will be some data loss will be there. Okay, so we are forced to use repeaters at least once in 100 or 150 kilometers. Okay, so what we can do is we are forced to use repeaters, or we are forced to find some repeaters to send this photons to over 100 or 200 kilometers. The next one is next challenge is channel loss. For every few kilometers, few kilometers of fiber absorbs some photons. Okay, lowering key rate. This is a major problem, major challenge. It's like uh, protector is acting like a thief. Okay, the medium is acting like a thief. Okay, so what we can do is we can use some satellite or free space links to bypass the loss. This is one possible research direction. The next one is detector efficiency. So in some cases, there may be some imperfect detectors may be there. So imperfect detectors will miss some photons. So obviously, each and every photon, collecting each and every photons is a very important task. If there is any uh, imperfection in detectors, obviously it is going to miss some photons. This will reduce the security margin. So Alice and Bob, what Alice and Bob think is there is some intruder. They have changed the photons. So obviously, what they will do is they'll try to send the communication again. Again, there'll be some photon loss will be there. Again, they think that there is some eavesdroppers as a intruder and change the message. So what we can do is we can go for better single photon detectors. We can use some better photon detectors to detect this, which is again the challenging task to design a near perfect photon detectors is again a tedious task. Okay. The next major challenge for us is cost and scalability. Obviously, you cannot design a quantum computer less than $100 million or $200 million. Uh, so it is the cost of building the quantum computer is somewhat high. So we need a specialized hardware for QKD, and also it is very expensive to maintain this cost. So obviously, an enormous amount of cost is involved in handling this QKD, the quantum things. So what is the alternative? Is we can go for a chip-based QKD for mass production. So this is one possible solution. Again, we are right now we are researching about chip-based QKD. Again, we have not yet achieved the success, complete success, or complete dominance in manufacturing. Again, we are in R&D stage only. Next is we have to integrate this quantum computing with the classical. So that is again a very big task. So you must make a QKD to coexist with the classical traffic on the same fiber. Again, that is a very big tedious task. So possible research we can go for a wavelength division multiplexing or plus standardized efforts. Okay. So let me put it in this way. QKD today's QKD is like an early internet in 1990s. It is slow, expensive, but rapidly improving. Okay, and on track to mainstream. So maybe in a decade or two, we'll have uh, maybe we'll have a quantum computer in our maybe in home itself. So next we are moving to the last part of my presentation, the future and post-quantum cryptography. So what happens is, so in the quantum computers threaten classical public key systems like RSA and ECC. And quantum cryptography uses physics of photons like QKD. Physics like some quantum cryptography uses physics like physics and photons like QKD. And what happens in PQC, post quantum cryptography, is it uses instead of using the sophisticated photons and quantum physics for building the quantum secure system. What happens in quantum post quantum cryptography is it uses mathematics for designing system, but this mathematics will be somewhat a new kind of mathematics, which even quantum computers will find difficult to break. And we have to implement this as early as possible, because even before a large quantum computer exists, harvest now and decrypt later attacks are possible. Right now it is happening. Adversaries may store today's encrypted data, which can be break the data. And we can go for some hybrid models like hybrid cryptography to tackle this problem. We can combine classical algorithm with quantum safe algorithm. Quantum safe algorithm. Say we can use TLS with both what to say, traditional algorithms like RSA and lattice-based key exchange. Even if RSA breaks later, data will be safe, obviously. And we can go for standardization. If it comes to standardization, okay, there is something called as NIST. NIST is dictating some PQC standards, which is expected to release soon. What is happening is it's like reinforcing what is happening right now is we are trying to reinforce a bridge which people are still using, still driving on it. You can keep the old structure working until the new stronger supports are full and ready. And that's it with my presentation. I rest my case. If there's any doubts, participants can shoot their doubts. I hope I have confused enough. I confused and you got confused and we both got confused. And I hope that you people will you people will start confusing others about quantum quantum computing. And if anyone has any doubts, they can shoot their doubts. I'll try to clarify doubts, or maybe I may confuse you again. I hope my presentation was not good for the past. Sir, back and code. So you are telling Rohit. Actually, right now I have a implementation source algorithm implementation. Right now, I'll please share your email ID. I will share the code which is available with me. So what happens is uh, uh, source algorithm can be used for breaking classical cryptographic algorithms. Actually, one of my friend has done it. They have used a simulator given by IBM. He used a simulator given by IBM and he implemented source algorithm. But unfortunately, few months back, the source algorithm library was removed from the simulator itself because more hackers are try to use this uh, code to crack the RSA algorithm. Okay, so it is possible to write code. You can either use Python, or my suggestion is you can go for Julia language. I think Julia language is a better choice for writing quantum programs. It is my observation that Julia is somewhat better when compared to Python. But the thing is, Julia right now, Julia language has a limited library only. That is the only problem with Julia. But Julia language is somewhat a decade old. But I think maybe in near future they will include some library for this also. If there is any other doubt, issue. Uh, okay. Someone has asked what is the post refers to quantum cryptography. So I think the post means the literal meaning after. I think so. It refers to the time after quantum computing became powerful. So what happens? Once the quantum computing computers became powerful enough to break the current cryptographic system? What happens? So obviously there will be some chaos and confusions will be there. So what happens? So post math, what is going to happen? So we are supposed to look for some alternate solution. One such alternate solution is mathematical solution. So mathematical solution for developing a foolproof quantum cryptography. And in a show, you can say that it is a future proof. Okay. Rohit, I'll drop the code within say 10 or 15 minutes. I'll drop the code, Rohit. You just let me notice. I think you can note this. Okay, Rohit, sir. I noted your email ID. I'll send the Python code which is available. Is there any other doubts? Okay, I think I have confused enough. So let me rest the case. So you got enough time to confuse yourself, and you can confuse your neighbors and friends with whatever knowledge I have shared with you today. So thanks for the opportunity. Thanks for I thank Sridevi Institute of Engineering and Technology for giving me the opportunity to deliver this lecture. I want to thank coordinators, Dr. Rajeshwari ma'am and another professor, I think Vasha from the same department, same SAT college. I thank both the coordinators and also the chief convener. Who is the head of the department of CSA department. I thank them. I also thank AACD for conducting such wonderful workshop for the faculty members, in which many faculty members will gather and share their knowledge in a common forum. Thank you. Thanks again.
Sir, Sampath sir, this is Professor Chetan from
Yeah,
State Institute of
please.
Engineering Technology.
Yeah, please tell me,
Sir,
sir.
one of my participants has shared one query, sir, Dr. K.S. Kiran.
Okay.
He is asking two electrons are entangled, whether energy change or spin.
Electrons are entangled, and whether the energy of changes or spins.
Yes, sir. Two electrons are entangled, whether energy change or spin.
Uh, in again, I'm not what to say. I'm not a very big expert in quantum mechanics. With the limited knowledge which I have, I can tell you that the both will happen. It depends on the scenarios. If in some cases the both will occur, sir. In some case, spin will occur. In some cases, some energy change will occur. Again, Professor, this is a very tough question. To be frank, the question may looks very basic. It is like asking what has happened if you add 1+1 or 2+2. But when it comes to quantum mechanics, okay, both will happen only if we observe it. Yeah, I can put it in this way. If you look at the light, okay, uh, if you look at the light, okay, I can claim that light is a wave. In a sense, light is a wave, but in other sense, light is also a particle. Okay, but I cannot claim that light is only a wave or light is only a particle. Light is both. So this is the answer for your question also, sir, also, Professor. Both will happen.
So, dear participants, if you have any queries, please kindly post in the chat box.
Again,
Sir, one of the
uh,
participant, Rohit,
again,
is asking.
Rohit,
Yes,
Rohit,
sir.
I saw your question. Due to time constraint, I will. I already. I think you already shared your email with me. I'll share my materials with you about post quantum cryptography. Because again, if I started to explain about post quantum cryptography, again it is another topic. It will take at least half an hour to not to complete the complete scenario. I'll share my number and email ID with you. I'm going to anyway. I'm going to send you. I'm going to drop my drop the source algorithm code to you. I will drop my number also. You can call me and we can discuss about. We can both confuse about confuse each other about post quantum cryptography. Okay, sure, sir. I'll share my email ID. This is my phone number, sir. 88382947. This is my personal phone number, so you can call me at any time. Usually during working hours, I'll attend your call. Thank you, ma'am.
Thank you, Sampath sir, for the wonderful session.
Thank you,
So
ma'am.
this was for today's schedule at the FDP, aiming the excel of a candidates in quantum technology, hoping for learning to be paid as a part of a further topics. This is shall call it for today. Thank you for all the attending for this session, and kindly fill the attendance and feedback form which is shared in the chat box. Thank you all.
Again, thank you all for listening to my confusing lecture for the past 1.5 hours. Thank you very much. And again, I thank the management and the faculty members of Sridevi Institute of Engineering and Technology. Thanks again. Have a nice day. Thank you.
Participants kindly fill the attendance form, feedback form that's shared in the chat box as soon as possible.
Dear participant, the session will be wind up in another 2 minutes. Kindly fill the feedback link as well as attendance link.